Your brain is a 3-pound marvel more powerful than any computer we've built. It lets you ride a bike, recognize faces, laugh, and wonder about the universe. Computers, made of silicon and metal, are fast at calculations but rigid and literal. The brain is flexible, adaptable, and messy, its greatest strength. What if we could build machines that learn and adapt like brains? This question drives the field of artificial intelligence, where we try to replicate the brain's learning using software and hardware. We're reverse engineering the most complex machine we know to build something new. The universe built a brain, and now that brain is trying to build another. In our quest to replicate human-like thinking in machines, we delve into the fascinating world of artificial neural networks. To build a computer that thinks, we use math and code, creating artificial neural networks, or ANs. These networks are the backbone of many advanced AI systems you see today, from image recognition to natural language processing. They allow computers to learn and make decisions in a way that mimics the human brain. Imagine connecting millions of simple units, each performing a small calculation, like Lego bricks, to build something complex. Each brick contributes to the overall structure, and together, they can create amazing things. These units, called nodes, are the fundamental building blocks of our networks, or artificial neurons, mimicking the biological neurons in our brains. They're designed to receive, process, and transmit information, just like their biological counterparts. Are arranged in layers, a structured approach to processing information. Input, where the raw data enters the network, hidden, where the magic of processing happens, and output, where the final result is presented. The input layer receives data, like pixels in an image or words in a sentence. Hidden layers process it, performing complex calculations to extract meaningful features. These layers can be many, allowing for intricate pattern recognition. And the output layer gives the answer, whether it's a classification, a prediction, or a generated response. Each connection has a weight, a numerical value, making signals stronger or weaker, influencing the flow of information. As data moves through layers, these weights determine the importance of each connection. The network learns patterns, identifying relationships and correlations in the data. Edges in images, shapes of objects, faces, recognizing individuals. By adjusting these weights, refining its understanding of the data. It's a massive organized game of telephone, where each node passes information along, building complex knowledge from simple signals, transforming raw data into insightful conclusions. This layered, bottom-up approach, starting from basic elements and building towards complex understanding, is the foundation of machine intelligence, enabling computers to perform tasks that once seemed impossible. ANs learn by transforming simple inputs, like raw sensory data, into meaningful outputs, such as predictions, classifications, or even creative content. It's a beautiful mathematical echo, a testament to the power of algorithms, of how our own minds work, inspiring us to create machines that can learn, adapt, and solve problems in innovative ways. Artificial neural networks are inspired by real neurons. Your brain has about 86 billion of them. Neurons receive signals through dendrites, process them, and fire if the signal is strong enough. They communicate via electrical signals and chemical signals across synapses. Artificial neurons mimic this. They receive numerical inputs, multiply by weights, and sum them. If the sum passes a threshold, the neuron fires and sends its output to the next layer. This is a simplified, mathematical version of brain activity. The brain is far more complex, but this model is a powerful starting point. We've translated the core idea, interconnected units passing signals, into computer code. This biological inspiration drives the intelligence behind modern machines. The human brain, a universe contained within our skulls, holds a profound magic. And the most remarkable aspect of this magic is its unparalleled ability to learn and adapt. It's a dynamic organ, constantly rewiring itself based on experiences and interactions with the world around us. At the heart of this learning process lies a simple yet powerful principle. Neurons that fire together, wire together. This means that when two neurons are repeatedly activated at the same time, the connection between them strengthens. Learning, therefore, isn't just about acquiring new information. It's about physically reshaping the brain. It strengthens certain connections, making them more efficient, while weakening others that are less frequently used. This constant remodeling is how we form memories, acquire new skills, and adapt to ever-changing environments. The more we practice, the stronger these connections become, solidifying our knowledge and abilities. Early computers, in their infancy, followed rigid, pre-programmed rules. They were powerful calculating machines, but lacked the flexibility and adaptability of the human brain. But the brain learns in a fundamentally different way. It learns from examples, from observation, from trial and error, not from explicit instructions. A child doesn't need a manual to learn to walk or talk. They learn by watching and imitating. Inspired by this remarkable ability of the brain, scientists sought to create artificial networks that could mimic this learning process. These artificial neural networks are designed to adjust their own internal connections, or weights, based on their experience with data. So instead of programming explicit rules, we train these networks with vast amounts of data, showing them thousands, even millions, of examples. Initially, the network starts with random weights, essentially making wild guesses and producing nonsensical results. But with each example it processes, it refines its weights, gradually improving its accuracy. It's much like a child learning to catch a ball, constantly adjusting their movements and hand position until they can reliably make the catch. The network adjusts and gets better over time. This iterative process of learning and refinement closely mimics the way humans learn, but with the precision and power of mathematics. This fundamental ability to learn directly from data without explicit programming is what makes neural networks so incredibly powerful and versatile. It's a revolution, a paradigm shift, in how we create intelligent machines, opening up possibilities we could only dream of just a few years ago. How does a network actually learn? By making mistakes and correcting them. It's like playing darts. You throw, miss, adjust, and try again. The network gets an input, makes a guess, and compares it to the correct answer. The difference is the error or loss. Training means minimizing this error by adjusting the network's internal weights. It's a feedback loop: guess, check, adjust, repeat. Each cycle, the network tweaks its connections, slowly improving. Like a sculptor refining a statue, the network shapes itself to fit the data. Over thousands of examples, it learns the patterns hidden in the data. This relentless self-correction is the heart of machine learning. Uno de los métodos más comunes, y quizás el más intuitivo, para entrenar una red neuronal, para enseñarle a realizar una tarea específica, es el aprendizaje supervisado. Este enfoque es fundamental en el campo del machine learning. Es como tener un maestro paciente, un guía que muestra el camino correcto. En este método, le damos a la red datos ya etiquetados, con la respuesta correcta. Es decir, cada pieza de información viene acompañada de su solución. Por ejemplo, miles de imágenes de gatos y perros, cada una con su etiqueta, indicando si es un gato o un perro. La red predice, basándose en lo que ha aprendido, compara con la etiqueta real, la respuesta correcta que le proporcionamos, y ajusta sus pesos internos, sus conexiones neuronales, según el error que ha cometido. Al principio, sus respuestas son aleatorias, casi como adivinar, pero con cada ejemplo que ve, con cada corrección, mejora gradualmente su capacidad de predicción. Aprende a reconocer patrones, orejas puntiagudas, bigotes característicos, ojos felinos, sin reglas explícitas que le hayamos programado. El aprendizaje supervisado está detrás de muchas aplicaciones: filtros de spam, traducción automática, reconocimiento facial. El ingrediente clave para que este método funcione es un gran conjunto de datos, de alta calidad y etiquetas precisas, que reflejen la realidad que queremos que la red aprenda. La máquina aprende con ejemplos, como un estudiante dedicado, bajo la supervisión constante de los datos, que actúan como un profesor que corrige sus errores. Así, la inteligencia artificial se vuelve cada vez más capaz de resolver problemas complejos y realizar tareas que antes eran exclusivas de los humanos. ¿Cómo sabe la red qué pesos cambiar? Con un algoritmo llamado retropropagación. Imagina una fila de personas pasándose cubetas de agua. Si falla al final, revisas hacia atrás para encontrar el error. Retropropagación hace lo mismo. Empieza con el error final y lo reparte hacia atrás, capa por capa. Calcula cuánto contribuyó cada nodo al error y ajusta los pesos responsables. Es como repartir la culpa y corregir a cada jugador del equipo. Así, la red aprende de manera eficiente, descendiendo poco a poco hacia un bajo error. Cada paso la acerca a predicciones más precisas. Es el motor matemático del aprendizaje profundo. Las redes neuronales ya no son ciencia ficción, están en tu vida diaria. Desbloqueas tu teléfono con tu rostro. Una red neuronal lo reconoce. Asistentes de voz, redes sociales y servicios de streaming usan redes neuronales para personalizar tu experiencia. En medicina, analizan imágenes para detectar enfermedades con precisión. En autos autónomos, procesan datos para navegar ciudades complejas. Predicen el clima, componen música y ayudan a descubrir medicamentos. Son expertas en reconocer patrones en datos complejos. Lo que antes era exclusivo de la intuición humana, ahora lo hacen las máquinas. Las redes neuronales están transformando la ciencia, la industria y la vida cotidiana. Vivimos en una era donde las máquinas empiezan a percibir y comprender el mundo. Hemos creado máquinas que aprenden, perciben y crean, pero ¿pueden realmente pensar? Algunos creen que, si la conciencia surge de la complejidad del cerebro, podría surgir en una red artificial igual de compleja. Otros piensan que la conciencia es algo especial, no solo procesamiento de información. Una máquina puede simular emociones, pero ¿puede sentirlas? Hoy, no tenemos una teoría científica de la conciencia. Las redes neuronales actuales son herramientas sofisticadas, no seres conscientes. No tienen deseos ni sentido del yo. Pero a medida que avanzan, la pregunta se vuelve más urgente. ¿Crearemos un verdadero compañero pensante o solo una herramienta brillante? El futuro depende de la respuesta.